I would like to start by thanking AMD and Cody for organizing the event. It's been great to be back at the States after 5 years, I think, or something like that, and meet people from the States again. And today I'm here together with Alejandro, that used to work with me at Citrix. We used to work together doing address space isolation last year, well, half a year maybe. And I'm here to present this work. I would start with a bit of a description of what is address space isolation and what is it trying to solve. Then we'll get a bit into the work that we have been doing together, the different items that we have been working on to get this done. And finally, we'll also look a bit into the next steps that we need to finish the project. So what's the purpose of address space isolation? The purpose is to make sure that only data that's needed by the currently running context is available. That means that anything that's not needed by the current context shouldn't be mapped into the page tables. The main thing with Xen here is that Xen itself doesn't have any sensitive information as part of the hypervisor. So basically all sensitive information is from the guest context. So what we would like to achieve here is make sure that there's no sensitive information mapped outside of the current context. The main benefit of that approach is that at that point, if we don't have any sensitive information mapped permanently into the page tables, we can remove a lot of the mitigations that we do on entry points for the speculative vulnerabilities. So that means that we can move all those mitigations that we would usually do at the entry points to the context switch between vCPUs. That's not only interesting in terms of performance, it also means that for new vulnerabilities, we may not have to do anything, or we may have to only change the context switch path, but that's a lot less than having to modify the entry points, which is a lot more work in general. The main design constraint that we have is that we would like to be able to mix domains that are using address space isolation with domains that are not using it. One example would be, for example, on a Xen server deployment or possibly XCPNG also. DOM0 is a trusted component, so it doesn't need all the speculative mitigations. Basically, we try to disable as much as we can from that. So in our use case, or in that use case, we would like to run DOM0 without address space isolation so that we still have the benefits of being faster, and all the other guests using address space isolation. So that means that we need to be able to mix and match ASI and non-ASI domains in the same system. I've also added a bit of terminology about what we are going to speak because, well, this is fairly known to people that do Xen development, but may not be known to people that's not so familiar with Xen. The direct map, I think, it's a terminology that's also used in other OSs, so it's probably known to other people. It's basically a region of the virtual memory address space that used to map all host memory. So it means that you can access any host RAM range using a virtual address without having to map it into the page tables and so on. So that's used more or less by any 64-bit operating system that has enough space to map all physical guest memory. That's the direct map. The Xen heap and the DOM heap are two terms that we use on Xen that are not found on other systems, I think. Xen heap means memory that's always available in the direct map. The direct map has a certain size, so if you have memory past that range, it's not mapped on the direct map because it doesn't fit. Basically, anything that we allocate from the Xen heap, it's permanently mapped. It's always accessible using the direct map. On the other hand, the DOM heap, it's different. DOM heap is not guaranteed to be permanently mapped, so you can allocate from the DOM heap, but when you need to access memory allocated from the DOM heap, you need to use a specific helper to access it, which is called map domain page. That page will create you the mappings if needed so that you can access that memory region. That's the main difference between Xen heap and DOM heap. And finally, the map cache is a scratch virtual address space that we use to create mappings as required by map domain page so that you can map DOM heap pages on demand. There's a bit of previous efforts here done by other people that are not at the Xen Summit. This probably all started after the first wave of speculative CPU issues in 2018. And it was started by Wei in Citrix and Server at that time, the secret free hypervisor, which then moved into, well, was the first step into direct map removal, which was continued by Hongyang in Amazon. They did, I think most of the series that we are trying to progress now is work from Hongyang and Wei at that point, a bit more from us maybe, but it's more or less like that. It's not that upstream. And then they also published a paper called Secret Free Hypervisor a couple of years ago. The threat model in that case was attacks between domains. So one domain trying to leak data from another domain. The problem with that approach is that you don't take into account that different CPUs inside of the same domain can have different security contexts. So you also need to protect against attacks between CPUs on the same domain. And that's something that was not considered as part of that work. Also, it had another limitation, which was the lack of protection of data on the stack, on the Xen CPU stack. Basically, the stack is always mapped. So if you spill data onto the stack inside of Xen, this data will be there forever. So you can still have crosstalk between CPUs because of that data on the stack. Now I would like to speak a bit about the virtual memory map in Xen. This is specific to x86. I think it's different on ARM, but I'm not going to speak about ARM because I don't know. So I'm just going to focus on the x86 one. So this would be the root level page tables. You have 511 and 12 slots here that you use to populate the page tables. Xen is a bit special in that regard because when you run pbguest, the virtual address space is shared between the guest and Xen. So that means you need space on the root page tables that's owned by Xen, and it's only used by Xen. So we picked those slots, 256 from 271, and those slots are owned by Xen. The guest can never use those slots. The rest of the root page table is usable by the guest. That's a very big limitation because we have a very limited number of slots that we can use on the root page table. And then inside of those slots, the first one is used by the machine to physical translation table that's shared with the guest. The next slot is used to map any ECAM or, well, what's called MMM CFG also, which are the PCI apertures that you use to access the PCI config space, the extended PCI config space. The next slot is the linear page table. This is, well, I don't know if you're familiar with linear page tables. They are a mess. But this slot it's used to point to itself, so you can access the PTEs of the page table to modify them. It points to itself, so then you can modify the page table without having to map it. It's a bit of a trick that some operating systems use in order to make changes to the page table faster without having to map it. The next slot, it's fairly similar to the first one, but it contains a pointer to the guest page tables when you are running in shadow mode. It's a very specific slot that's used by Xen when running guest in shadow mode to be able to access the page table entries of the guest in order to create the shadows. So as you can see, we already wasted 4 slots and we haven't done almost anything by Xen. So I mean, it's fairly limited, the space that we have. The next slot, it's important for us. It's a per domain slot. It means that each domain has a different page table here. That slot is owned by the domain. That one is important for us because we will reuse it for the purpose of ASI. The next slot, it contains some space for BMAP, which are permanent mappings, the Xen text, the Xen data, and also the page info frame table, which contains the entries of the page info struct. And finally, the last slots are used by the direct map. That's the thing that I mentioned before, which is a permanent mapping of all the host memory. In green, I've marked the slots which are relevant for ASI, and we'll now see why they are relevant for us. So the first problem that we have with ASI is that on x86, we are not capable of creating per CPU mappings. Every time we create a mapping, it's at least shared by all the vCPUs of the domain. So that's a problem because we have crosstalk between CPUs. We create a mapping on one CPU, but the data that we map can be snooped from another CPU. That's not intended, basically. We want to avoid that. One of the main problems that we have with creating per CPU mappings is that the root page table on PV mode is controlled by the PV guest. And that means that the PV guest can use the same root page tables on multiple vCPUs. And that's a big problem for us, because if the guest uses the same root page table on multiple vCPUs, we cannot create per CPU mappings because the root page table will be the same across multiple CPUs. And that's a big problem for us. So the first thing that we need to do is to enforce unique root level page tables. So basically what we have to do is to, when running PBGuess, we have to create a shadow of the root page table so that we use a different page table on all the different physical CPUs. Even if the guest intended to use the same, we basically shadow this and create a copy that's internal to the CPU. That's not a lot of trouble because that's already done by XPTI, so we can use a lot of the logic there. So it's not a big deal, but it still needs some work so that we can use that. And what's the point of having a unique root level page table per CPU? At that point, we can convert the per domain slot into a per CPU slot, which means that we have one slot of the page table that can become per vCPU, which means that we can now create mappings that would be visible only to that physical CPU. And that's very important to us because it prevents us from crosstalk between CPUs if we can create mappings that are only visible by the current CPU. The drawbacks of this approach is that, of course, we have to shadow the root page table of the PBGuest, so that would be a bit of performance impact. But as I said, it's already kind of the same that we do with XPTI, so it's not that much. And also, since we now move the per domain slot into a per vCPU slot, the memory consumption used by the page table structures will increase a bit because we have to allocate on a per vCPU basis rather than a per domain basis. But I think that's not that different. And well, as I mentioned, this is only interesting. Well, this is only because of PBGuest. HBM guest always have a per vCPU root page table. So that means that each HBM guest vCPU has a different root page table. So that's not a problem. If you run only HBM guest, you don't need to care about shadowing the root page table. So this is a bit of an example of how it looks like now. That would be mappings created by map domain page, for example, on the different vCPUs of the same domain. As we can see here, this is all shared. So the mappings, even if not used by the other CPUs, they are also accessible because they are created on the same page table structures. We can see that those are shared between domains, between vCPUs on the same domain, but are not shared across domains. So if you create transient mappings on a CPU that's running a different domain, those would not be shared with the other physical CPUs. And we want to get to a point where it looks like that, so that you can create mappings on the different physical CPUs and they are not shared at all against the other CPUs. In that case, we can see I've used different colors to mean that the memory map is different. So for example, we can see here we have the same region being used by two physical CPUs, but the contents of those mappings will be different because the page table structures are no longer shared between them. It also means that when you unmap something, you only unmap it on the CPU that had it mapped before. It's not shared anymore, so the structures are completely isolated between them. And then there's also what I mentioned before, the problem with the per PCPU stacks or the Xen stacks. This is this is kind of what triggers all the other work in part, so that we need to be able to map the CPU stacks in an isolated way, which means that you can, one CPU should not be able to read the stack from a different CPU. Why is that so important in Xen? It's for two reasons, basically. The first one is that when you run Xen, of course, you will spill data into the stack. You may spill registers from the guest into the stack and so on. So that would be a problem. The second reason is that by default, when you enter Xen, all the guest general purpose registers are dumped into the stack. So basically, every time you enter Xen, all the general purpose registers are copied into the stack. And that's obviously quite dangerous when you're doing ASI. So the solution in this case is to allocate the stacks from the DOM heap. If you remember from the previous slide, the DOM heap is the memory that's not permanently mapped. So we need to allocate from that part of the stack, from that part of the memory. One of the consequences here, and it's one of the, well, that will need more work, I think, is that when you now, if you are into that model where you no longer have the stack of all the CPUs on the system permanently mapped, when you get an API, you may have trouble accessing the data by that API. An API is an interrupt from a different CPU. It might request you to run some function or to process some data or something like that, but that data may be on the stack of the remote CPU. So the workaround that we did on the initial series was to map the remote CPU stacks when you get an interprocessor interrupt. So basically, if this CPU would get an interprocessor interrupt from this CPU, before executing the code of the interrupt, it will map the remote CPU stack in order to access any data. That's obviously not ideal because it means that you still transiently map another CPU stack and you map it fully. So you have access not only to the data that was intended to be used by that CPU, you access all the stack data. So I think in principle, what we would like to do in the future is to change a bit how we do interprocessor interrupts and to know which memory needs to be shared with the remote CPU. So use some kind of bounce buffering maybe to a shared memory address or something like that, so that you know that the memory you are sharing with the other CPU is exactly just what you want to share, not the full stack. And of course, all this logic to do per CPU stacks also adds a bit more complexity to the context switch, because every time you context switch a vCPU, you need to make sure that the incoming CPU has the right stack map. So basically, you need a bit more logic in the context switch path to make sure that the stack is mapped. And yeah, once you get to that point, it's fairly nice. I've got a prototype of that I sent to the list, and it works, so it's not so bad. And now I will hand over to Alejandro, which will speak about the work done to the direct map removal. Is it working?
Hello, hello.
Yeah. Maybe not. Yeah.
Oh. Okay, I'll just use this. So, well, first of all, thanks a lot, Roger. He did a lot of the all of the previous work on per vCPU mappings, and that is a very, very, very complex. Sorry for remote.
Would you like that one then? I think.
Yeah. I'll just grab it like that. He did all of the per vCPU mappings stuff, and it is really a really complicated intertwined piece of logic with PV and everything. So really good work. Now, of all the sins that Xen might commit in terms of keeping secrets map at all times, the direct map is by far the worst offender. As Roger mentioned before, the direct map holds virtually all the memory in the host system. Unless you have a really insanely large system, it will really map everything. So that is the first thing to get rid of. Back in 2019, when we first proposed the secret-free hypervisor idea, the idea itself was, let's remove the direct map. And that seems like a pure there's purity in the idea, but it causes some problems, as it was very quickly found out. Essentially, when you want to deal with any sort of hypercall, suddenly you have to map up to 20 something times in order to find the last page. Then you read it and you find that you need to do it again. So getting rid fully of the direct map is complicated. What's the next best thing we can do? The next best thing we can do is remove the secrets. And well, we already have a pretty good idea of this. As Roger mentioned as well, we have Xen heap, we have DOM heap, and we have already established that if you want something to be secret, it should be in DOM heap and not on Xen heap. So let's remove the DOM heap from the direct map. That's how you end up with a direct map that has gaps like the one at the bottom, rather than the one on the top that has all the host memory. One interesting side effect of going through this approach and the design constraint of keeping simultaneously domains with and without ASI support on the same running system is that suddenly you really do have two representations of the direct map, one that is fully populated and one that is not. This also means that when you want to allocate something from the Xen heap from, say, your DOM0 that has the full direct map, now you have extra bookkeeping to do. Now you have to map your Xen heap mapping into this sparsely populated direct map that is not assigned to yourself. So there's complexity. Performance, we expect performance to be affected to some extent, but on the other hand, there is some concurrency matches that suddenly disappear. So we'll see after we manage to run some benchmarks. So in terms of what to hide, what not to hide, what's a secret? What's a secret? Clearly, guest memory is a secret. And if we allocate guest memory from a DOM heap, that's covered. Guest PTs come from guest memory, so that's pretty much the same thing. But as we start going down the turtles, you quickly find out that, well, is that a secret, really? And the P2M is one such example, in that you might be tempted to think, well, it's really just the way we represent and the guest physical address space. Why shouldn't it not be secret? Why should that be available all the time? But you can think about it the other way around. If it was not secret, and there are really no secrets, it's just a bunch of addresses. It's what is the next page table? What is the next page in this traversal? Not making it secret. Making it secret makes a lot of performance impact. So we chose not to do that. Other cases are even more complicated. Struct vCPU doesn't have inherently much in terms of secrets, but for historical reasons, many registers that actually live in the CPU are stored in the struct vCPU rather than in a separate structure. So many of these things will need to be moving because whatever is secret must live contiguously with other secret stuff. So we can allocate it from the DOM heap. Everything in red can be moved into separate pages very easily. Things in yellow depends. The struct vCPU has some fields that need moving, but sometimes it's complicated because the code might or might not expect it to be mapped at all times. Transient allocations are really on a one-to-one basis. We have plenty of examples in which Xen has this very confidential data over here, and then it tries to load it into the vCPU or the other way around, but then finds out, oh, actually, I need to operate on it. I need a copy. I'm going to take a Xen heap allocation to copy it there, which is not great for hiding things. It's like taking something out of a safe and then put it in display. There is one last thorn in this whole thing, because if we manage to compartmentalize all the secrets in single pages, such that I can use this map domain page and map domain page helpers to access them, we already have the infrastructure. The code is not quite there, but we have the infrastructure to do that. Xsafe is one special case in which things get quite complicated. The way x86 manages floating point saves and restores from the core is by using the xsave and xrestore or fxsave or fxrestore instructions. Those instructions take a parameter that's the virtual address of the buffer from or to which you are going to be copying the FPU data. And at the moment, that is less than a page. But with the upcoming AMX coming into play, that is going to grow, and it's going to grow to be bigger than a page, potentially bigger than a page. At which point we need something that allows us to do a map domain pages. I'll mention it later, but we will need something that akin to map domain pages to be able to map things contiguously, even in the when using the map cache. So essentially, as far as sensitive information goes, it is really a matter of going into the current struct vCPU and looking at everything and seeing how it's allocated, and anything that uses xzalloc, anything that uses xmalloc, anything that uses Xen heap alloc pages, or whatever it's called, move that to use an allocation of DOM heap pages instead. And if it's a very, very small allocation, find it a way of moving it together and aggregate it with something else so we can properly hide it in that new per vCPU area. These might or might not be simple. Some cases are reasonably simple. General purpose registers is relatively simple. It's already disaggregated in a separate structure. Some parts of the FPU register state are very, very helpful not to hide, because they do tell you whether you need to map the others or not. So there is no automation here. It is a human eye going over everything and finding out what needs to be moved and what doesn't. And this is what I mentioned before. This is a simplified version of what essentially happens during a live migration when you try to fetch the state for the floating point unit to send it to the stream. You have something in DOM0 that will ask, can you please give me the FPU state of that vCPU that belongs to that domain over there? And then Xen will pick that up. And under an ASI configured system, it would need to map the FPU state. And actually, no, it wouldn't work on the live migration. But generally, when you do want to, maybe on context switch, when you do want to dump the state in the running CPU onto an actual buffer, now you need that buffer to be contiguous. You need something different, maybe a map domain page is an extension of the current map domain page, or some form of fixed map that operates on the per vCPU area that we can map and unmap at pleasure. But we will need some means of performing this physically plus virtually contiguous, because it must be both, because it must also work on non-ASI domains. We must have a way of doing this and dealing with transient allocations so that there are no copies into non-safe memory. Roughly, that's the existing work items. Largely, the direct map removal series has already been worked on quite profusely. It sits currently at a B5, I think. And per CPU mappings, it's, I don't know, V2, V3? V2. They are largely independent. The direct map removal largely misnomer because it's simply a removal of the DOM heap in the direct map. Is already done and has been tested to work. Same for the per CPU mappings. Once they are both combined, we will need to start going through the process of migrating everything. I sent a few batches already to add a few wrappers for the FPU, for FPU mapping and unmapping. Then we will have to go through all the hypercalls and all the entries and exits and make sure that we don't do exit alloc transiently to copy confidential data where it doesn't need to be. And at that point, we will be in a position to disable the security mitigations because everything is safe, right? and do some benchmarks, performance analysis, see if the work we did. It is true that many of these things introduce performance penalties, but sometimes the work works out and suddenly you reduce contention because you don't have a shared map cache. You reduce contention because you can allocate from an allocation piece that belongs to your own CPU, and that's it. So who knows? We'll see when we get there. As reference, there are other ASI implementations in the works. Linux ASI does not resemble this idea. They operate on a different mental model, and they're working on keeping two sets of page tables, one that is secret free. And in general, if you enter the kernel, do something over there and find that there's nothing you don't need access to secrets, then there's no mitigations to be done. And if you do need access to some secrets, then it can flush everything on the way out. The idea is to move frequent operations out of requiring any secrets at all. They are suffering a bit with performance, but I believe the latest patches have made it less problematic with the file cache. We'll see how our plan pans out in the end. And I think that's all. Those are the links for the latest versions of the for the patch series. So if there are any questions. Yeah, Jan?
Early on on the slide where you have shown the basic x86 memory map, there were two green sections and a white one with VMAP in it alongside Xen image space and so on.
You mean that one?
Is there? Yes, that one. Is there a reason we consider VMAP safe?
Well, we'll need to do on a case-by-case basis. I think that's part of the work that Alejandro was doing and analyzing it. And anything that's mapped.
Well, it is not. If you map something in VMAP, you cannot map secrets in VMAP.
Yeah, I basically would have expected it to be at least light green.
So if you need to map secrets, you would use map domain page, and that would go automatically on the slot 260. I don't want to call it the per domain slot.
Yeah,
it would go on that slot that with Rogers patches would be per vCPU, so that would not be.
Importantly, the VMAP space is in the same same top level PTE as everything else. You cannot make VMAP have a different scope to the rest of the Xen text and section. The only thing you can do is move data out of the VMAP section into some other address range.
It's not mapped on green because it's not part of the per domain transition to per vCPU or the direct map removal. Just memory that's sensitive, it cannot be mapped on VMAP. That's basically
okay.
That's why it's not green, because it's not affected by the force to remove the direct map or convert per domain into per vCPU.
Okay. And then later, towards the end of the presentation, you talked about the plan of removing mitigations from the entry paths. Is that as the wording basically says, intended mainly for performance analysis? But if the performance analysis is to yield any real-world results, what would the entry point paths actually look like in the end? Because we can't remove mitigations blindly from there, as long as we have non-ASI domains as well.
So bear in mind that it's not so much removing the mitigations altogether as it is moving them to the context switch path. So whenever you're changing domains from a ASI to a non-ASI domain, non-ASI to an ASI domain, you would go through all the mitigations to make sure that all your branch history buffers, and then everything else is properly flushed.
Yeah, but I mean, I think Jan is worried that you still need to keep them there, but make them conditional on a runtime basis.
Yes,
Because you have ASI and non-ASI domains. So
and the making conditional of at least some of them is problematic.
yeah, we'll see. Still have to get there.
So
Yeah,
what?
because now we use alternative to make those conditionals at
Yeah,
init time, but we can no longer do that.
There is one pretty clear possibility. Compile the entry path twice, once with and once without
Yeah.
mitigations.
It's important to say that the thought going into this is really, if you look at the past, I would say 8 years, some of us have been working since mid-2017 on these. It's getting quite long. What we're seeing is that routinely since then, we're getting 3 or 4 brand new variations of speculative attacks every year. They are still coming at 3 or 4 a year. Basically, it's impossible to isolate the state in the processor. Otherwise, it would have been fixed in the next generation of CPUs, and it's not. The idea of ASI is to get to the point where you think that there is nothing interesting that can be got by speculation. As much as anything else, it is it's an expectation that this will protect against issues we don't yet know about without needing to make further changes.
Now thinking about it, we already have some of the mitigations that are dependent on runtime using the CPU flags, the IBPB, and quite a lot of them are already.
Some of them are
because
conditional.
We them for them zero basically on the server.
Yeah,
Yes.
I mean, in the end, as I said, some of them are sensitive and therefore cannot be just skipped over by conditional branches or whatever. But some others are quite okay. Okay, thanks.